Hello, calculus students. Well, I left out a few details in the previous video, so I thought we would go back and look at some of these problems in a little bit more depth. And so what I've done over here is I've written some of the tests and or methods that you might use for thinking about convergence or divergence of these series. And of course, in some cases, if you're lucky, you can actually tell what the exact sum is. So, and we'll talk about, which tests are helpful and which ones are not helpful for particular problems. Now, if we look at the problems in the top row here, it turns out that 3 of these actually involve geometric series. And that's this one, and this one. And so we'll talk about that first. And it turns out 2 of those will converge, and you can actually find the exact sum. That's this one here and this one here. And then one of these will diverge, and that's this one here. So let's just recall very briefly. So if I bring this down here, so what the geometric series formula says is if I have a sum that's of this form, and here we're going from n equals 0 to infinity, and we have a first term, and then we have a common ratio raised to the nth power, that this could, well, one of 2 things could happen. Either this could be a over 1 minus r, and this is if absolute value of r is less than 1, and otherwise it diverges. Otherwise the series diverges. Now if I look at this formula here, this series here, I see that it's of that form, where here I have, so if I write this here, this one, n equals 0 to infinity, and here I have just 2/5 raised to the n. Here, that first term a is just 1. That's messy. Let me fix this. That first term a is 1, and the common ratio in this case is just 2/5. So you know what this is going to be equal to then. It's just 1 over 1 minus 2/5. And then similarly with this one here. So if I write that one out, it's actually close to the same thing. This is 0.4, and that's 0.36 there. So here I have sum n equals 0 to infinity, and I have 0.36. I guess I forgot my 0.36. I have my 0.36 raised to the n. And so this will be equal to 1. That's, again, the first term is 1 in this case. And that's over 1 minus 0.36. And those are easy. So we've got this one here and this one here. And we've seen not only that they converge, but we've seen what their sum is. Now, the other one, this one here, I told you about, this one diverges, and that's because the common ratio is too large. It's 1.67. So here we have, I don't know why I'm really copying this over here, but this just diverges. And the reason why is because 1.67 is bigger than 1. So the common ratio would have to be between -1 and 1 in order to converge, strictly between -1 and 1. Now let me see if my purple marker works here. Let me, maybe it's better to record this as saying, so this one converges. Why don't I just circle the ones, well, let me see. How do I want to do this? I guess what I'll do, let me see if my orange marker works. My orange marker works, and I'll circle the ones in orange that converge. and that you can find the sum. And so that's those two. I don't know how well this will show up in the video. And then ones where you can, where it converges, but it doesn't, you can't find the sum easily, then I'll circle it with the purple marker. And then ones where it diverges, then I guess I'll circle with the black marker. So we found that this one here diverges. So we've got 3 of them. And so let me clean this off. Now for the this one here, this series, this you could immediately use what's called the p-test. And this is derived from the integral test. So you remember the idea here, if you want to think about it in terms of the integral test, is you're comparing this to so you compare this to an improper integral. And if you read about the hypotheses for the integral test, I mean, we talked about this in class, but the function that you're integrating in the improper integral has to satisfy certain properties. I mean, the way they usually write the test in the book is they have it be continuous and monotone decreasing and larger than the series, and the series has to be positive and the integral has to be positive. And so you essentially trap the series between the coordinate axis and the function that's defining, well, that you're taking the improper integral of. And so in this particular case, it would be natural to compare. So here's the series again. The series is n equals 0, or rather 1, I'm sorry. Of course, 1 it has to be. So 1 to infinity of 1 over n to the 5 halves. And it would be natural to compare this to integral from 1 to infinity of 1 over x to the 5 halves dx. And that's an easy improper integral to do, because you can just use the power law to do the indefinite integral, and then, you know, it's easy to see that it comes out to a finite answer. I'm not going to work out those details because of time, but you could easily work out those details. However, I mean, what you really do in this case is you just look at the power, because you remember with the what the p-test came from is you had, if you're looking at this integral and you have, say, 1 to infinity and then you have 1 over x to the p dx, you remember that this converged if p was bigger than 1. So this converged if p is bigger than 1. And so you can use that to immediately conclude that the series will converge if the power here is bigger than 1. And of course, 5 over 2 is bigger than 1. So you could just look at the power, compare it to 1. If it's bigger than 1, now notice this power is in the denominator, right? If this was n raised to some power, if it was in the numerator, then it would have to be less than -1. But so long as it's in the denominator, then you want the power with the n to be here bigger than 1, and then it will converge. So you know it converges. Now this kind is not easy to actually find the sum of, if you even can do it. I mean, you remember I told you, some of these where you have powers are known what the sum is. I mean, for instance, I showed you before this one, n equals 1 to infinity 1 over n squared. This is the famous pi squared over 6. And then 1 over n cubed. Nobody knows. So this is 1 over n cubed. Nobody knows. And then this one kind of fits in between. So this is the one that we're looking at. This one kind of fits in between. So it wouldn't be easy to actually think about what the sum of that is. And so for that reason, I will put it in purple, because we know it converges. We know it converges, but we don't know what the sum is. And maybe I didn't spell that out when I was talking about earlier, when I was just saying what the powers were. So the most succinct or concise way to say this is that this particular one, n equals, what is it, 1 to infinity, 1 over n to the 5 halves. This converges by the p-test. Or you could use the integral test, so that would work. So the integral test would work. Now you could ask, well, would any of the other tests work? And yes, it would actually. I mean, you could use a comparison test here or a limit comparison test here. It's possible to think of such things, things to compare it to. But that's essentially because all of these involve comparing a series to another series or something. So anyway, that gives you an idea of what happens with that one. So we have it circled with purple. That means converges, but we can't easily tell what the actual sum is. Okay. So then let's move on to this one here. Now this is just really bad notation, you know. It's a unfortunate way of writing notation with these sort of archaic root notation appearing in there. So this one here, it would be better, just so you don't confuse yourself in terms of notation like this, to just rewrite this. So this is the way it's originally written, the fourth root of n cubed in the denominator. What does that mean? Well, what it means is just n equals 1 to infinity of 1 over n raised to the 3 over 4. It's a nuisance because these kind of change order when you look at it like that, right? I mean, it's like, you know, if I was looking at this, n equals 1 to infinity, what would it be if it was just the square root? Well, square root, that really means you have a 2 here for the root, right? And you have a 1 here for the exponent in there, and so this is the same, of course, as this n equals 1, and then we have n to the 1 half. So whenever you see a root and a power like this, you can take whatever's inside the root, and that's the numerator of the fractional power, and whatever the root is, that's the denominator of the fractional power. That's what it comes out to. But anyway, ignoring that commentary, we have now a power that's less than 1, and so this diverges by the p-test, because it's less than 1. So we can put a black box around that, and that's our first 5 problems.